We're live.
Excellent. I am only partially alive, I think.
Where were you?
I was in Israel. I am in the middle of doing 4 continents and 8 cities in 8 weeks. So my brain is a bit meh at the moment. So I'm like still trying to figure out what show are we about to record.
This is Astronomy Cast.
Yes.
It's a show about space and astronomy. You're the co-host, Dr. Pamela Gay. My name is Fraser. Hello.
Hello.
We're going to talk about gravitational assists and orbital transfer maneuvers, which people just can't get enough of. It's all they want to talk about on my Q&As.
Really?
Oh yeah. We could do 20 episodes about gravity assists. That's all they want.
Why?
What about a black hole? Could you do a gravity assist around a black hole? How does it work? Yeah, I know people.
Only if it's moving.
People want to know. People really want to know.
Are they just playing not much Kerbal?
Yeah. No, they're super excited by the idea of gravity assists. So,
people, I love you all, but you're weird.
No,
you're very weird.
Love it. Okay, here we go. Hello to Ben Appleby and CWP and Gordon Dewis, Jamie S., James Haney, Johnny Zed, Larry Beckham, Nancy Graziano, Noel Ruppenthal, Stephen Angus, Steve Heistand, Thermophile, William Bacon, and Zapfan. I saw Johnny Zed come in, Larry Beckham come in, Matt Fulton. People are popping in now. Citizen Case, hey, how's it going? Right on. A lot of people who can't normally join us are able to join us at this wacky time. So,
welcome everyone.
Yeah. So how is your time?
I am good for the next 56 minutes.
Okay, me too. That sounds good. So we can go for the full 56.
Yeah.
Gordon, do you see that? We're weird. Pot meet kettle. You're black.
Well, yes. Yeah. Yes, I agree with that. However, for different reasons.
Now, have you got like a big chart that'll let you tell me what the different numbers are to go?
I was not anticipating this would include numbers.
People want numbers, but okay, we'll do what we can.
I was fully expecting to discuss the science and the physics without numbers.
All right.
Okay.
Hello, Eric Cardoso. It's gonna happen. Hey, Warbash.
Okay.
Thomas Traniker. It's Graziano. Did I already say Nancy's name? Anyway. Whenever you're ready, we can do this thing.
I was waiting for you to ask if I was ready to press record.
Are you ready to press record?
I am.
Here we go.
Pressing record.
Hello, Chad.
Hello, Chad.
Astronomy Cast, episode 484, Transfer Orbits and Gravitational Assist. You want me to do that again?
Yes, that was not normal.
Ready? Astronomy Cast, episode 484, Transfer Orbits and Gravitational Assists. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, the Director of Technology and Citizen Science at the Astronomical Society of the Pacific, and the Director of Cosmic Quest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. I really feel like I don't have a long enough title, though. That's for sure.
You know, when I was in undergraduate school, I was told that you have increased amounts of power according to how many keys you have, to a point at which the fewer keys you have, the more power you have. So the person who has one key to unlock all the things has the most power.
Right.
That may be you.
If a person has no title, do they have the best title? Good question.
Possibly.
Right. Sounds good. I have no news this week. Nothing super interesting. You're on the road like crazy. We're recording this in just this brief moment in between wheels down and wheels up.
It's true. I am just home from Israel, where I got to hang out with Yoav Landsman, one of the friends of both of our shows. And I'm getting ready to leave for Japan, where I'm going to see all the good folks behind the International Year of Astronomy back in 2009. And we're going to be working on planning new and exciting things. And then I'm back for like a week and I go to San Francisco.
Whew.
Yeah. But I can record Astronomy Cast from San Francisco.
That's true. Yep. Speaking of, if you want to get around in the solar system, you'll want to take advantage of natural gravitational speed boosts and transfer orbits. Whether you're heading to the outer solar system or you want to visit the sun itself, the planets themselves can help you along in your journey. All right, Pamela. Now, I mentioned this sort of before the show, the fact that people love the idea of gravitational assist. It's like, I don't know, it's like free money. It's like winning the lottery. And they love the idea. So let's get into gravitational assists and transfers. Now, we talked about gravitational assist a long time ago, and this was one of those times when I legitimately didn't understand how this worked, and you explained it to me in a way that I finally understood it. And so this idea of gravitational assist, right? And I think this is where a lot of people have the problem understanding it, is that it makes sense. You know, let's say you're flying your spacecraft to Jupiter. It makes sense that your spacecraft is flying towards Jupiter, and as it falls down into Jupiter's gravity well, it speeds up and speeds up and speeds up. But then as it flies away from Jupiter, it's being pulled back towards Jupiter, and so it's going to slow down and slow down and slow down. And so when you think about this sort of dropping into a gravity well and back out, you would expect that the speed boost that you would get would then be canceled out by the speed unboost. How does a gravity assist work?
I love how you do like 90% of the explanation and then you're like, and what's the final 10%? So it turns out the gravitational assists only work if you're working with a moving object. So for instance, within our own solar system, we can change our direction using the sun, but we can't boost our orbital velocity using the sun, because relative to the rest of the solar system, for all intents and purposes, the sun is not moving. Now, Jupiter is moving, and the fact that it's moving makes all the difference in the world. So if you sneak up on Jupiter, which isn't hard because it has no observational abilities, if you sneak up on Jupiter as it's orbiting in the same vaguish direction that it's moving around the sun, you will spend more time as you're catching up to Jupiter getting pulled into Jupiter and pulled along the orbit with Jupiter than you spend running away from Jupiter. It's that excess time as you're moving in the same direction as Jupiter where you're gaining from its orbital speed and getting to add some of that to your own speed.
But the planets themselves are orbiting, as the further you go from the sun, the planets are orbiting more slowly.
Yes.
So how can you know, if you're orbiting the Earth and say the Earth is going, I don't know, 30 kilometers per second, and then you leave the Earth on this big long trajectory, you fly past Jupiter, it's going more slowly. How does that give you a boost?
It's the amount of time that you're falling into its gravity well. So as you're catching up to it, it's going, come on, you can do it, pulling you in with gravity. That pulling you in with gravity over the long period of time that it takes for you to catch up. Each moment that you're working on trying to catch up to Jupiter, it's pulling you a little bit further and pulling you a little bit further. And then it's as you race away, and you spend much less time racing away. It's that integrated time that's longer catching up than it is running away.
And so something has to pay the terrible price for this, right?
Well, Jupiter in theory slows down a little bit, and it actually happens in reality, but not at a level that we can measure. Because let's face it, the mass of a spacecraft is awful tiny compared to the mass of Jupiter. So while Jupiter does give up some of its momentum, that loss is not a huge concern to that giant planet.
All right, so let's talk about a couple of missions that used gravitational assists in the past. And the first one was what? The Mariners? What was the first spacecraft to use a gravity assist? Hold on. I know the answer to this. Mariner 10.
Thank you.
Well,
okay,
no, hold on.
Thank you.
Mariner 10 used a gravity using the interstellar. I don't know if they use an actual gravity assist. Well, let's talk. Why don't we do it?
I was all ready to talk about Voyager too.
So let's talk about the Voyager.
Okay.
So I'll ask the question again. All right.
Okay.
So the most famous example of spacecraft that used gravity assist were the Voyagers. Tell me about that.
So Voyager 2 is perhaps the best example. It left Earth, was on a nice happy journey through the solar system, caught up to Jupiter, and turned almost a right angle as it slingshot around Jupiter and made its way straight off towards Saturn, where it made another massive turn to get flung off towards Uranus. And from Uranus, it was almost a straight line. We had this glancing blow past Uranus with only a slight turn coming, and then it headed out towards Neptune. And it was this amazing alignment of the worlds that Voyager 2 was taking advantage of. And Voyager 1 took advantage of it as well. It was this amazing alignment of the worlds that was what caused them to race to get the Voyager program done when they got it done. Had the worlds not been aligned so beautifully in their orbits, allowing all of these different gravity assists to take place, Neptune would not have been on the possibilities list. And we would never have had one spacecraft be able to make such a grand tour through the solar system.
And I mean, you've probably seen the animations of them doing this, right? Where
yes,
the Voyagers go past Jupiter, and then they get this, you can see the slingshot. They go faster, and then they take another trajectory around Saturn. Voyager 2 heads off to Uranus and Neptune, and Voyager 1 just sort of heads off into deep space. Interesting side note, I don't know if you knew that Voyager 1 could have made a trip to Pluto.
And they decided not to because they needed to get a little bit better of a look at those moons.
Yeah, they wanted to get a look at Titan. And the horrible irony is that Titan was too foggy for the Voyager spacecraft to see it, and so Cassini had to be the one that did it. All right.
We did learn something. We learned it has an amazing atmosphere. It was just with sadness that we learned that it has an amazing atmosphere at the cost of Pluto.
Yeah. All right, so that's a good example of a spacecraft that, that's a very famous mission, but others have sort of done famous gravity assists, not because they wanted to go really quickly, but because they wanted to be able to get there at all. And a good example of that was the Galileo Mission.
Right. So launched back in 1989 on the Space Shuttle Atlantis. It was originally planning to do what's called a Hohmann Transfer orbit. This is how we normally get to Mars. This is where you hit your nice circular orbit around Earth, then boost your velocity such that our position on Earth is the closest point on the orbit to the sun, and that furthest point from the sun is going to be when they hit that next world that we're planning to get to. And in the case of a few Mars missions, I mean, hit that world quite literally. But ideally, you get there and you slide straight into orbit. And the original plan for Galileo was to slide right into orbit. But there was problems. Our our ability to use the space shuttle changed between when they designed the Galileo spacecraft and when they launched the Galileo spacecraft, and we were no longer taking space shuttles to as high in orbit. And with these changes, the energy just wasn't quite going to be the same. So they basically visited more objects than seems rational in our solar system, by which I mean they got to Jupiter by way of Venus, which is not a path anyone would ever really expect.
Right, and explain that, right? So, you know, we talk like that simple idea of the Voyager flying out, picking up a speed boost from Jupiter, and then, you know, Jupiter paying the terrible price and getting slowed down a tiny little bit, and then it slingshotting out into space. How could it use something that's closer to the sun? And like it used Earth as well, but it launched from Earth. What?
Right. So it launched from Earth, was in a orbit around the Earth. It then increased the size of its orbit so that it went out past Venus. So that is bigger than going around the Earth. It got a gravity assist from Venus, which slung it a little bit faster, moved it along, and so now it's in this orbit that started at Earth, included Venus. It's now heading back towards Earth. It got some more gravity assist from Earth and then continued off on its way until it eventually, very far in the future, ended up slowly making it to Jupiter.
Right. I'm still, you know, we'll probably need to move on, but I think, you know, for a lot of people, that how you can get that sort of stealing of momentum from an inner planet is the part where their easy understanding of how this works starts to go sideways.
So the way to think of it is, while you should push a swing just as it's about to hit its highest, well, just after it hits its highest point, to add velocity as it goes down, you can add velocity to it at any point and you're still going to increase how high the swing goes, as long as you're pushing in the same direction the swing is already going.
Right.
So with Venus, we're going along in our orbit, and because its gravity pulled us in the direction it was moving, in the direction we were moving, that extra pull was just like running along as someone's on the swing, giving them a little bit of extra force the entire time. It's not a lot, it's not ideal, but it totally gets the job done.
So what is this sort of the theoretical limits of what this technique can give you? Like, could you just keep going back and forth in the solar system, ping-ponging around until you're going the speed of light? What are the limits?
Well, the fullness of time doesn't quite allow you to get there. You can continue to increase your speed until you're going the speed of the objects that you're stealing energy from.
Compared to the sun.
Well, okay, it's more complicated than that.
See?
Yeah. So you start out usually going faster than the objects. It's the whole momentum thing. You can't steal all of an object's momentum. You can slowly, and momentum is mass times velocity. So the thing that makes gravitational assists work is spacecrafts have little tiny mass, planets have big mass, spacecraft have large velocity, planets have not as large a velocity, but still large compared to me sitting in my chair. And that velocity that they're going around the sun is, as long as we're moving with that and not at a right angle, right angles don't work, we're good. If we're going against it, we can slow ourselves down. Now, as you're ping-ponging around, you have to be careful of a couple different things. One, don't launch yourself out of the solar system.
Mm-hmm.
So you can't exceed the escape velocity of the solar system and not have a plan for turning yourself around and
Right.
keep ping-ponging around.
Right.
So just that's a mathematical
Right.
difficulty.
And just to give people some context, right, the escape velocity of Earth is about 8.5 kilometers per second, and the escape velocity of the solar system is about 16 to 17 kilometers per second. So that's your window. Could you scale this up for even further, though? Could you use,
Oh, yeah.
Another star? Could you use a black hole? What are the limits of this?
There's no limit as long as the other object is moving. That's the whole catch. If it's stationary relative to the system you're flying through, it's not going to help you. So if you're flying around inside our galaxy, you're not going to be able to gravitationally assist yourself around the black hole in the center. You can change your direction. You're not going to gravitationally assist yourself. But all the little stars all over the place, those are totally useful. All of the stellar mass black holes all over the place, totally useful. You just have to, well, gravitationally assist yourself out of the solar system first.
Right. Now you can use gravitational assist in reverse as well, which is that you can use them to slow yourself down. And I think a good example of what that is the upcoming Parker Solar Probe. I don't know if it's exactly slowing itself down, but it's getting itself to a very difficult orbit, which is very close to the sun. So how would this process work in reverse?
Well, in this case, you simply go against traffic. You fly in the direction so that your motion looks like you're heading towards a head-on collision with a planet, and then you miss. And as you're getting accelerated towards that head-on collision, you're getting accelerated into the planet's gravitational field. But the amount of time it takes you to get there, since it's a head-on collision, is shorter than the amount of time it takes you to go, oh my gosh, I didn't actually get hit, and fly away. So as you're flying away with it behind you, you moving past it, this amount of time is prolonged, and that's where all of the slowing down takes place.
Right. And so in this case, you're actually speeding up its orbit.
Yes.
And it is doing the reverse. It is slowing. So you're kind of giving it a push, which is awesome.
And it's all about the momentum in this case. Physics requires momentum to always be conserved, and you can do all sorts of remarkable things this way. But what's cool is you're also changing the angles on everything. So while we often think about the speeding up and the slowing down, every time you see Voyager 2 making that almost right-hand turn as it makes a bank shot around Jupiter, it's also changing the direction of the orbit. And this is key when we start thinking about what happened in the early solar system as we boosted various moons, various asteroids, all sorts of things into all sorts of different orbits. It was all the same principle.
Right. All right. So now this is kind of half of the conversation. The other half is to talk about transfer orbits. And you mentioned briefly the Hohmann transfer.
Yes, this is the most common type of transfer orbit that we think about because it's in a lot of ways the lowest energy kind of transfer. You fire your engines once when you're at that closest point to the sun. If Earth is where you're starting and you're trying to move outwards, and then you fire them again to move into orbit as necessary once you get to your furthest from the sun point at either Mars or Jupiter or Saturn. And it's this simple change your orbit once, set yourself going, and then just correct your orbit when you get where you want to be that makes it so simple to do, such a low energy orbit. Now, the thing with the Hohmann transfer orbit is you do have to remember that you're actually slowing yourself down if you want to go to an inner orbit. So you can use it in both directions. We can use the Hohmann orbit to get to Mars. We can use it to get home. It's just slow.
Right.
Slow happens.
Right. It's the trick with the Hohmann transfer is that it is your slowest but the least amount of propellant that you have to use. And as you said, right, you're firing your thrusters when you're in orbit around Earth, say, at this perfect time. This is the key, is that you need this window.
Yes.
And then you fire your thrusters, and this puts you on a new, essentially, orbit around the sun that intersects both Earth and the target that you're trying to get to. Say it's Mars. And then when you get to Mars, you fire your thrusters again to get caught and go into orbit around the planet. And you've used the minimum amount of propellant. But as you said, and this is why, like, we can only fly to Mars every couple of years.
And it's one of our great frustrations with everything in the solar system, because the alignment we got with Voyager 1 and Voyager 2 isn't an alignment we're going to get again in our lifetime. So there's certain exploration missions that we just can't wait for the planets to get back where they are, and we can only launch in so many windows to get to Mars. And it's just a huge frustration because alignments are fairly rare. But we do what we can and keep a constant eye out for when is that prime time to get to Jupiter, when is that prime time to get to Saturn or Mars.
And when is that prime time when you can fire a spaceship past the 4 giant planets in the solar system?
Yes.
Oh, not again for another couple of 100 years, unfortunately.
But luckily they got it done when they needed to get it done.
Yeah. The amazing thing about that mission was that they didn't even know that they were going to be doing that full grand tour until they'd kind of already launched. They knew it was possible, and they'd raced to get that time frame, but they didn't know that they were going to for sure do it. And so in the end, they did get the green light and were able to extend the mission to add Uranus and Neptune, which is always so fascinating. Now, you talked about the Hohmann transfer, which is this really, and again, there's tons of animations on the internet. I apologize that this is a podcast, because this is the kind of thing that's, for example, if it was the Guide to Space, we'd show you a pretty animation, but just imagine you leave Earth and you fly on this big, long, sort of circular orbit, and you reach Mars. Let's talk about some other transfer orbits. The one that I love is the free return trajectory from the moon. I think it's the most fast. It saved Apollo 13. Oh yeah, I love that transfer, that trajectory.
Okay, so do tell. I was ready to talk about a bielliptical, but it sounds like this one is your heart and soul.
It's not. I just love it. but this was this idea that when you fly to the moon, there is, as one extra layer of safety, is that you can follow a trajectory where you're able to return back to Earth. You sort of do this figure 8 around the moon and are able to come back, and you sort of catch the Earth where it's moved a little further in its orbit, and the moon has moved around a bit in its orbit, and you can kind of make everything lined up. And it's a safety valve if there's a problem with your mission, and they used it in Apollo 13. They weren't able to go down, they weren't able to land. They used the free return trajectory. They went around the moon, used it as a different kind of slingshot to kind of get thrown back towards the Earth, and were able to return the astronauts safely. And if they hadn't built that trajectory into account, they probably wouldn't have gotten those astronauts back safely from that mission. So I really love sort of that free return trajectory. But let's talk about your next transfer orbit.
So one of the orbits that has always left me going, that makes absolutely no sense, but it still gets used, is the bielliptic transfer orbit. This is an orbit where, say you start off in a fairly low Earth orbit, nice and happy circular, and you want to get yourself into a slightly larger circular orbit. It turns out one of the ways to do this is to put yourself into a giant elliptical orbit. So you start off small circular orbit, fire your engines. The point where you fire your engines becomes your closest point to the planet Earth. You're now launched off into an elliptical orbit. You will return to the same distance you start at. But say you don't want to return to the same distance you started at. Say you want to return to a slightly further out orbit, but not a lot further out of an orbit. When you're at your new point in your elliptical orbit, furthest from the Earth, you just fire your engines a little bit. And as you fall back to Earth, you'll fall back, but not back to your starting point, to a point further out than your starting point. Fire your engines again to circularize things. And this is one of the lowest energy ways to move yourself between two circular orbits. And it actually can require less change in velocity than the Hohmann transfer maneuver, which to me does not intuitively make sense, but the math makes sense.
Right.
And my stomach yells at my brain, and the brain wins.
Right. Well, I think the most fascinating one, and it's sort of the longest slow, like if you've got nothing but time, then you want to take the Interplanetary Transport Network. Have you looked into this?
I haven't.
So it's essentially this idea that you can sort of make your way up to the Lagrange point around a certain object, say one of the Earth Sun L2 Lagrange point. And at that point, you're kind of drifting away from the Earth at that point. And then you can sort of slowly make your way with very little propellant and get caught by the Mars I'm trying to think, the L1? Yeah, the L1 Lagrange point, the Mars Sun Lagrange point. And you sort of drift your way in. And you can actually go from world to world throughout the entire solar system, either direction, with almost no propellant. The only downside is it takes a ludicrous amount of time. So if you want to go from Earth to Mars, you can do that for free if you can get up to the Lagrange point. It just takes 10,000 years. And longer if you want to go from Mars to Jupiter and Jupiter to Saturn. It's crazy.
Let's maybe not do that.
Right.
But be in total awe of the first person who figured out the mathematics on that.
Yeah. There's there's a researcher at NASA JPL, and there's this great graphic of the Interplanetary Transport Network, and everyone's super excited about it until they find out how long everything takes. It has been used a couple of times because there's sort of smaller versions of it that you can use if you're trying to go to asteroids that are close to Lagrange points that are already available to us. So if you want to go and visit a various near-Earth asteroid or things like that, you can do it within a couple of years with almost no fuel. But to do like significant, but even that is way too long. Like you could just take the Hohmann transfer and be there, relatively overnight. But if you got nothing but time and you don't have fuel, then you can follow the Interplanetary Transport Network, but one of the interesting ideas about that is just that there is material that could be flowing from world to world because of the way these gravitational balances work out.
And that's kind of amazing.
Yeah.
And at the end of the day, the magic of all of this is, and by magic, I mean the sufficiently advanced science of all of this is, if you have all the time in the universe, you can get anywhere with very little energy requirement. The trick is this ping-ponging around doing the gravity assists takes time. And if you want to get somewhere fast, the way you do it is you accelerate constantly and then deaccelerate constantly. And that at least gives you gravity.
Yeah. Awesome. All right. We got one more episode in this series, and that'll be next time.
Sounds great, Fraser.
Right. See you then, Pamela.
Okay. Bye-bye.
All right.
I have to say, one of the most amazing things that's happened in all the years of us doing this is watching you get more and more advanced in what you know.
I learned it all from you.
Well, some of it you learned from Kerbal and from researching for your
for being a space journalist for 19 years.
Yeah.
It definitely had a hand in it.
Because when it comes to this stuff, you know your spacecraft way better than I know spacecraft.
I don't know if I know. Man, we just know different things. Like the thing is that everything's a rabbit hole, right? And
yes.
And so it just depends on whether you've gone down that specific rabbit hole enough times that the information is locked in your brain. So
yes.
So that's the only, that was 484, right? Yeah.
Yeah.
Yeah. Yeah. So I happen to have more of this stuff, you know, in my head. I can talk at great length about the plan to send drilling robots to Europa right now, if you want.
That's awesome.
Or just wait next week when the episode comes out. Well, it's so funny. I mean, one of the great things about doing these shows live is you really know what people are interested in, and they just keep bringing up the questions again and again and again. And so I just like, I'm like, okay, I'll do an episode on drilling, how you get down under the water under the ice on Europa. And so, you know, I sort of dug up the research paper, dug up the proposal, and went into the gritty details. And the part that's amazing is how accessible this idea actually is. Like, people have built heat-based drilling robots that go in Greenland at about 10 meters per hour.
Oh,
and
God.
they just use heat to sink their way into Greenland ice, spooling fiber optics behind them. So these,
We need that ice.
well, you want to examine that ice.
Yes,
Yeah.
I know. Yes.
Yeah. So, but anyway, so that's it. So I now find, like, I get most of my ideas for the shows just based on what everybody wants to talk about. They want to talk about artificial gravity. They want to talk about biosignatures. So anyway, that's my advice. All right, I just saved my thing, so let's take some questions. There was a good question.
I accidentally lost my pop-out chat.
Okay.
It's here somewhere.
Arjone asked if you wanted to use solar system using the lowest amount of fuel, then would you use gravitational assist? Assume time is not an issue, so I believe I answered that question. And then Stephen Angus wanted to know if the transfer orbit is done in the opposite direction, which I think we got to. Nancy is wondering, would it be advantageous to combine an ion propulsion engine with the Hohmann Transfer orbit, or would it take so long to get anywhere that it's not feasible to do this?
So the thing with the Hohmann Transfer orbit is you want a massive firing at perigee and apogee.
Right.
Whereas the ion drive is just like, I'm going to slowly accelerate for a long time. And so no.
Right. And that's the kick. You need that kick.
Yeah.
So now you can make up for it again with time. I mean, so over time, the ion engine is going to give you the speed boost that you need.
Yeah.
At a fraction of the propellant price than the big Centaur upper stage that you're going to use, but you need to take your time and follow a different trajectory.
And things like the ion drives really are absolutely perfect for what Dawn did, where you're moving between objects that don't have a large difference in velocity between them, and you're just going to do a slow, constant acceleration to get from the inner object to the outer object.
Right. Ben Appleby wants to know if I had $60 million, could I buy myself a Falcon 9 and put it in my garden, in your rocket garden? Now, there is a rocket garden at the Kennedy Space Center.
There's also one at Marshall.
Right. And I don't know if there's a Falcon 9 in there. I don't know what you would be able to pay for to get a used Falcon rocket. I'll bet you could get it for a lot cheaper than that. There's one sitting outside in Hawthorne in Los Angeles, outside the SpaceX facility. So you can get so they took the first Falcon to successfully land. They set it up there. But my guess is that you could get a Falcon for a used Falcon that maybe they didn't want to fly again. Or maybe like wait until it's flown, whatever is the length of time, you know, like maybe 100 launches, and then you could probably get one. Put in a price now, and like I bet you could do like, you'd almost make like an insurance program. Like you say, okay, if you launch this specific rocket 100 times, then I get it for $100,000. Musk could be up for that. He'd think that was so cool.
Yes. Yes. So I saw a kind of hilarious tweet the week that there was the big New Space conference down at Kennedy, where there was a Falcon 9 parked directly in front of the space shuttle engines that they have in front of the space shuttle experience. And the tweet was along the lines of, "Hey, Musk, you're parallel parked."
In fact, Citizen Case, who's in the chat right now, drove past, lives in LA, drove past that and got me a picture of that Falcon from the SpaceX headquarters so that we could add it to a picture. So
that's awesome.
Christy wants to know how advantageous it is to have launch sites closer to the equator. Is it a substantial gain?
Substantial is in the eyes of the beholder, but yes, it's I would say it's a substantial gain. I honestly have always been very mystified at how far north the Russians launch from.
Right. When you think about, just imagine this, right? Like when you are launching from the North Pole, you have to go from 0 to 28,000 kilometers per hour.
Yes.
Which is the orbital velocity, and you have to just brute force that. And
yes.
when you are launching from the equator, you're already going about 1,000 kilometers per hour. So you have one less 1,000 kilometers per hour that you have to go to get into that low Earth orbit. So you decide if that's enough of a gain for you. For most people, it sure is, because it either lets them put a heavier payload or lets them use less fuel.
And the way to remember it is it goes as the cosine of your latitude. So cosine of 0, you're at the equator, that's 1. By the time you get to just 30 degrees off, you're already at 0.8. Cosine of that is 0.87. So that means you're going at 87% of that 1,000 miles per hour.
Right. Now you're talking about, people are talking about how the Russians, it's surprising how far north they launch from. I mean, they launch from about as south as they can get within their territory down in Kazakhstan. But the Russians also really pioneered other orbits. They weren't transfer orbits. We didn't talk about them in this, but we have talked about them previously. Like was it the Molina?
Yes, those highly elliptical orbits where you're going at roughly geostationary rates when you are closest to the Earth, and then you zoom out and zoom back, and that allows them to get these essentially communication satellites, weather satellites working at their extreme northern and southern latitudes. But it does take them a little bit more energy to get them there because they are launching from 45 degrees north latitude.
Right. And then, of course, if you're doing polar orbits, which are very useful orbits, then the rotational speed doesn't help you at all. Unless the Earth is spinning this way. Right.
and that fits with the recent SpaceX launch off the coast of California.
Right. Well, sometimes they have to do just a brute force launch, and they're not able to recover the lower stage, although they're trying.
Yes.
Right. The other, oh man, there was another question. Okay, so Glencaster asks, so a solar sail can break orbit and a magnetic sail can't, because a solar sail uses light pressure from photon pressure and the mag sail uses the solar wind. That is correct, I believe. So in other words, the Van Allen belts are protecting, the magnetosphere is protecting and blocking the solar wind. So if you've got a magnetic sail going around, or an electric sail going around the Earth, it's not going to be able to pull any thrust from the solar wind until it gets outside of the magnetosphere.
Yes, that is entirely true. There's also magnetic tethers, which are kind of cool, but you can't leave Earth orbit with those either. They're just cool.
Yeah. Ben Appleby is asking, how come all the planets in the solar system are in roughly equatorial orbits? Why aren't there any planets in a polar orbit?
because something really, really fundamentally bad would have happened to put a planet in a polar orbit, or we would have had to steal it from another solar system, which I don't put past our
Right.
sun. No, so the way our solar system formed was in what's called a solar nebula model. And you take a large cloud of gas and dust. This is called a molecular cloud. And under normal circumstances, they're kind of hanging out, minding their own business, nice and stable, balanced between gravity trying to collapse them and their own internal pressures from the temperature of the gas holding them out. Now, if something comes along and shocks that cloud of gas and dust, getting it so that the molecules and stuff collapse past that point where the pressure balances against gravity, once that collapse starts, the whole thing's collapsing. And unless that shock is exactly along the center of mass, it's going to start rotating, just like if you flick at a pen sitting on your desk, it's going to start rotating unless you hit it exactly in the center. That rotation ends up flattening out the cloud of gas and dust the same way that pizza dough tossed in the air and rotated flattens out. It's the exact same physics. With everything flattening out, you end up with the planets forming inside of the disk, all moving basically the same direction, all moving basically the same plane. And all of the abnormalities of things like Uranus that's knocked over on its side, Venus that's rotating in the wrong direction, all of those seem to come from traumatic events, as near as we can tell from our modeling, where interactions between different worlds had the effect of flipping things sideways, moving them around, and changing their orientation relative to that original spinning blob of gas and dust.
Right. I mean, one of the things that I kind of like about that question is how it's kind of like by seeing that solar systems don't line up with the Milky Way, you get a sense that their formation was independent from the formation of the Milky Way. Like it
Yes.
gives you a clue. If a thing is all orbiting together in this flat pancake, like say the Milky Way, then its formation was somehow connected because everything is in this same plane. But when you look at the sort of jumbled up solar systems throughout the galaxy, then that gives you a sense that, okay, they're not connected. Otherwise, they would be aligned in some way. If all the solar systems were all the same alignment within the plane of the Milky Way, then that would give you a different theory on how solar systems form.
What was particularly awesome is looking out at the globular clusters. There's two different families of them that are named after a scientist. Whoa, sorry. So we have the Oosterhoff type 1 and the Oosterhoff type 2. And at this point in my jet lag, I don't remember which is which, but what I do remember is they have different metallicities. This means they have a different content of their stars. Some have more metals, some have less metals. And those of one Oosterhoff type are orbiting the galaxy on average in one direction, and the others are going in the other direction. And so it looks like we stole a good chunk of our globular clusters from something else through a collision that got everything going in the wrong way around the galaxy.
Right. All right. So Stephen Angus is talking quite a lot in the chat here about his gravitation drive, and this is not the right forum for that. I know you figured something out and you're really excited about it, but you know, this is not the right place to bring it up, and we're not the right people to help you out with that. The best thing to look at is one of the engineering journals. If you've got something that is sort of in the realm of like aerospace, there's some really good aerospace journals that you want to look at. If it's something more in fundamental physics, you want to go with one of the fundamental physics journals. And, you know, physics, oh man, what is it? Physics B? What is the name of that paper? Physics Papers?
Physics Review
Physics
B.
Review, yeah, B. And those are all sort of about specific fundamental physics. And I think those would be sort of the best place to go if you want your ideas to be taken seriously.
Yeah. I can only really like stars.
Stars, yeah, exactly. Yeah, for me, I'm just a journalist.
Yes.
So, and I'm a computer scientist, not a space scientist. Bill Griswold is asking, did I dream that deuterium might be used to help melt ice on Europa? So, can you think of uh, how deuterium would contribute? I can't think of a way that you would. I mean, you could create some kind of deuterium reactor or something.
I think this is an engineering thing. Because I'm seeing a couple of different things on drill designs using deuterium.
Oh, okay, okay.
The deuterium has a lower fusion temperature than hydrogen does. So I don't know. But yes, from a quick Google, there were some drill designs back in 2010 based on deuterium.
You weren't dreaming it. By Gab Tier 11, is it possible to deorbit an outer icy moon to a collision path to Mars? That way we would have liquid oceans, thicker atmosphere, and some more gravity. Thank you. That was the other thing I forgot to mention. People love transfer orbits, and they want to just smash planets and moons into each other for fun and profit.
Yes, you can do this. Yes, you can, but should you?
Right. Yes. Totally should.
Mars might have life. Let's not kill it all until we figure that out.
So let's assume that both Mars and, I don't know, Europa have been studied very carefully, and we're absolutely certain there's no life on either one. They are just raw material.
Then sure.
It's like asking, can I squish a snowball and a rock together? The answer is yes.
Yes, you can.
Yes.
It will change the orbit of Mars. So use your power carefully.
Right. So there may be some orbital mechanics to do after you smash these moons together. Or Mars and this moon together. Right. Okay.
So I recommend sending both Europa and Enceladus so that you can recircularize the orbit.
Do one then the other. Okay.
Yes.
I mean, I think that I think both I and the audience appreciate your kind of open-mindedness about this. That the actual implications. So here's the problem, right? Is that the solar wind is continuing to bombard Mars with its onslaught of radiation, and anything you do to try and improve the atmosphere, if you put more,
it's just temporary
water, it's going to be temporary, and it will sort of send out. It's going to spray the hydrogen out into the outer solar system, and it'll be gone forever. So until you can get some kind of magnetosphere that's going to be able to block the solar wind, nothing that you do to try and improve Mars is going to be permanent. And that's really the challenge, is to, and the amazing thing is that if you actually put this, if you put a fairly small shield at the L1 point between Mars and the sun, and you block the solar wind from hitting Mars, it will actually naturally outgas, build up the density of its atmosphere, warm itself up, its ice caps will melt, and it will actually warm up pretty significantly. So that's what you got to do first. All of your astroengineering challenges need to start with Mars, with you blocking the solar wind.
And this brings us back to the minor problem of we still need to solve the radiation problem just for a spacecraft. We can't solve it for a spacecraft yet. And we can't even think about solving it for a planet. And so I don't know how we're getting to Mars yet.
Yeah. Well, you're just going to enjoy cancer.
Die. Yes.
You're going to increase your risk of cancer on the way to Mars, and then you're going to dig underground and you're going to live in a cave. That's your plan. And maybe get cancer.
Can I stay home?
Yeah, I'm totally going to stay on Earth. Like I get that some people really, I I made a terrible mistake. We did the weekly space hangout last week, and we had someone who works at NASA, but he had spent several years in Antarctica. He'd spent like, I think 5 years, 5 whole seasons in Antarctica over the winter times. And it was fascinating to hear his experiences. But I would have loved to have asked him, like, if you want to go live on Mars, what advice do you have for the person on what it's like to live in Antarctica first? And that was sort of because Mars is so much worse than Antarctica.
Yeah.
Zephan saying that we didn't get to the Oberth effect when we were talking about gravity slingshots. No.
Sorry.
In fact, you even mentioned it, that we were going to talk to it, right? Okay. All right.
Sorry.
Okay. Apologies.
We can fix that in tomorrow's episode.
Sure.
If someone reminds me.
Right. Noel Ruppenthal. Oh, sweet, you're still live. We are still live. Larry Beckham says,
I am about to go live as soon as this is over on twitch.tv/CosmoQuestX, where I'm working on finishing up a variable star simulation. So
awesome.
People probably just got notifications about that because that starts in 2 minutes.
Okay, I got 2 more things to say. One, Motorhead says, let's fix Earth's issues first. Motorhead, I'm going to blow your mind. What if you get all of the heavy polluting industry off Earth and you put it into space and you make Earth better? You go to space and you make Earth better. You make Earth better by going to space, because Earth really should have one job, which is to be awesome. Anything that takes away from Earth's awesomeness needs to get off and get into space. Be gone.
Yes.
Chris G says, I know the James Webb Telescope is going to be huge for astronomy. Can you briefly explain how big an impact this telescope will have? You have 45 seconds. Go.
It's going to allow us to see the first stars and galaxies forming and see Earth-like planets around other stars that are far enough away from the star to like actually be seen. And we can't see any of that right now. And so we don't know how solar systems and stars and galaxies originally formed. And it will answer that stuff, we hope.
Yeah.
In 45 seconds.
Nicely done. All right. I think it's time to wrap this up. Everyone, thank you so much for joining us. We appreciate it as always. Go join the WSH crew. Go to wshcrew.space and join the community. Be part of the chat. We're in the chat. Hang out with us. Hang out with everybody. And just enjoy space. Now, join Pamela over on Twitch as she, I don't know, codes up some Python for astronomy purposes.
It's Java, but yeah.
Okay.
Yeah.
Java. All right.
So twitch.tv/CosmoQuestX starting pretty much now.
Right on. Thanks, everybody.
Bye-bye.